given a straight line charge. Represented by the equation x minus x naught by a is equal to y minus y naught by b is equal to z minus z naught by c. Uniform charge density rho L. Now carefully look at it. At any point x naught, y naught, z naught, if you are asked to determine the field intensity, the integration will become clumsy because you should say at any x, y, z in which x is fixed, y and z are dependent variables because of this equation. I have to consider a differential element at any x, y, z. I should talk about the vector from a general position to x naught, y naught, z naught. And dl is not dx. Use dl as root of 1 plus dy by dx whole squared. X and y relation is there seen. Plus dz by dx whole squared dx from x limits from minus infinity to plus infinity. And because it is oblique charge, you have to evaluate every component. Integral corresponding to every component. Carefully listen. The mathematical procedure becomes clumsy. We know the procedure. If we want to determine the electric field intensity up to a point because of infinite line charge, where that line is oblique line in which x, y, z are related through the line equation. In this particular case, we have to evaluate all the three integrals because in general it will have all the three components to determine the field intensity at any point because of uniformly charged infinite line charge. The procedure followed is this. Consider any infinite line charge. The discussion that we had yesterday says what? On the plane perpendicular to this line charge at any point, if I consider a circle, the field intensity everywhere is radial and will have same magnitude. Not only that, at any point on the cylinder circle surface of radius r passing through the point of interest, and having the line charge as its axis, the field intensity in general is radial. The field intensity in general at any point is radially outside, given by the unit vector dropped from the foot of the perpendicular, dropped from the point towards that. If I know, I need to calculate only the magnitude of the field intensity. Radial component only will be there. I need to know the magnitude of the field intensity. Because the field of infinite line charge has cylindrical symmetry, I need to consider a simple consistent case in cylindrical coordinates. where the infinite line charge. Only if it is of infinite length, I can use this. In finite line charge, why not put the limits and then integrate? In this case, at any point, this is the point of interest. For any point on the circle of radius r having the center on the line charge, on the plane perpendicular to the line charge, I'll say I will consider this as z is equal to 0 plane. Now I will consider dz at any z having the charge rho l dz. Concentrate now. Because the field is cylindrically symmetric, the vector from the differential element to the point of interest, irrespective of where it is on this circle, is what? The vector is minus z a z. I think I told it sincerely. Minus z a z. I have come till this point. This is if this is at a distance r plus r arrow minus z a z plus r arrow, irrespective of the point where it is on the circle of radius r. Now, what is electric field intensity dE bar? dE bar is equal to rho l dz by 4 pi epsilon minus z az plus r arrow by r square plus z square whole power 3 by 2. Here also E bar is equal to, there are two integrals in which z by r square plus z squared is odd function of z. Because the line charge is going from minus infinity to plus infinity, I need to evaluate only radial component. Because of which E bar is what? Rho l r by 4 pi epsilon integral minus infinity to plus infinity dz by r square plus z square whole power 3 by 2 arrow. Az component will not be there, we know. There will be no vertical component. Here, luckily, even the mathematical function that we have, z by root of z by r square plus z square whole power 3 by 2 is telling that it is the odd function being integrated over the symmetrical limits, because of which it is 0. Put z is equal to r tan theta. Put z is equal to r tan theta. Rho l r by 4 pi epsilon. Integral dz is r secant square theta d theta. I'm doing this because it is important for us to know. Standardize it. Divided by r cubed secant cubed theta. Because of which it is a rho. Rho l by 4 pi epsilon r integral cos theta d theta from minus pi by 2 to plus pi by 2 in this particular case, it is clear, is sin theta from minus pi by 2 to plus pi by 2 is 2, because of which it is rho L by 2 pi epsilon or a rho. At any point on the cylinder of radius r having the line charge as its axis, the field is radially outward. Assuming rho L to be positive, we are deriving it. It is a vector relation derived. If rho L is positive, it is indeed along a rho. If rho L is negative, you have to substitute rho L with that negative value and say that it is in the opposite direction. At that point along a rho. A rho is what? How to get a rho? In general, I have a point of interest. From that point, drop the perpendicular onto the line charge. Look at the foot of the perpendicular. Get the vector from foot of the perpendicular towards the point, divide it with its magnitude to get the unit vector towards that point, which is a rho. Now, what is the information given by this? I will just use this. The magnitude of the electric field intensity at any point which is at a distance r from the infinite line charge of charge density rho L is rho L by 2 pi epsilon r. And it is radially outside to the cylinder passing through the point having the line charge as its axis. Means what? I have a line charge, normally oblique line defined not in other coordinate systems but Cartesian coordinate system, rho L. Line passing through x naught, y naught, z naught, and then actually having the direction ratios A, B, C, and all, that's fine. If I want to determine the field at a point with coordinates x naught, y naught, z naught, what is that I have to do? I should draw the foot of perpendicular, drop a perpendicular onto the line charge. Get the coordinates of the foot of the perpendicular xp, yp, and zp. Determine the vector r bar. Modulus of r bar is the distance of the point from the line. And the electric field intensity E bar is equal to what? In Cartesian coordinates I'm writing, but I am using the derivation that we did and say that it is radial line, along the radial line. This definitely is the cylinder passing through this point, part of the cylindrical surface, and r cap is a rho. A rho is equal to r cap, because of which electric field intensity is rho L by 2 pi epsilon mod r bar whole squared into r bar by rho L by 2 pi epsilon mod r comes. A rho is what? Unit vector, unit radial vector is what? R bar divided by modulus of r bar, because of which it should be a vector. Modulus of r bar whole squared is just a number. It is becoming vector because of r bar. Please check. So this is extremely important for me. I know that wherever it is, if I have an infinite line charge, the expression for the field intensity at a point in cylindrical coordinates is the same for all points on the cylinder passing through the point of interest x naught, y naught, z naught, having the axis line charge as its axis. Now, one problem for a general case we will do. Maybe that really makes you comfortable. Suppose I have a line. Infinite line passing through, let us say 1, 1, 1. Having the direction ratios 1, 2, 3. With rho L as the charge density. Ultimately, I will give a number to this rho L. So many microcoulomb, coulomb, nanocoulomb for the sake of problem per meter. I want to know the electric field intensity at this point with coordinates. Let us say 1, -1, 0. Just for the sake of talking about it, I want to first of all check whether this point 1, -1, 0 lies on the line or not. The line equation of this line is what? X minus x naught, x minus 1 by a, which is 1, is equal to y minus 1, y naught by 2, is equal to z minus 1 by 3. X is equal to 1 says 1 minus 1 by 1 is 0. Y is equal to -1 says minus 2 by 2 is -1. This point is not satisfying this equation. Check it. The point 1 -1 0 is not satisfying this equation. Is not satisfying the line equation. If you substitute 1 for x, -1 for y, and 0 for z, the values that I get are not equal, because of which it is not lying on the line. Now, there is a problem. I want to find out the intensity of electric field intensity at that point. I need to find out the distance of the point from the line. The general point on the line is x naught, 1 plus AR. A is 1. Y coordinate is 1 plus 2R. Z coordinate is 1 plus 3R. We spoke about line equation. If a point lies on it, they should all be equal and equal to some value. Because of which the general point on the line is 1 plus R, 1 plus 2R, 1 plus 3R. Now the direction ratios of this line are the difference in the respective coordinates in the same order. 1 plus R minus 1 R. 1 plus 2R minus of minus 1 is 2 plus 2R. 1 plus 3R minus 0 is 1 plus 3R. Are the direction ratios of the perpendicular dropped from the point of interest onto the line? Because this is perpendicular to the line, we need to find out that R for which it is perpendicular by taking the perpendicular relation of direction ratios where A1, A2 plus B1, B2 plus C1, C2 is equal to 0. R is such that R into 1 plus 2 plus 2R into 2 plus 1 plus 3R into 3 is equal to 0. Which gives R plus 4R, 5R plus 9R, 14R is equal to, correct? Minus 4, minus 3, minus 7. R is equal to minus 0.5, correct? Check it once. Please check quickly. R, 4R, 9R is 14R, plus 4 plus 3, that side it is minus 7. R is equal to minus 0.5. Because of which, what is the coordinate of the foot of the perpendicular? R is equal to minus 0.5 says what? 1 plus R is 0.5. Come on. 1 plus 2R is what? 1 minus 1 is 0. 1 plus 3R is 1 minus 0, 1 point, minus 1.5, because of which minus 0.5. Check it once. Is the coordinate. They are the coordinates of the foot of the perpendicular. Now you know the distance of the point from the line. What is the distance? This vector is 1 minus 0.5, 0.5 AX minus 1 AY plus 0.5 AZ. Because of which the distance, now R bar is this, divided by mod R whole squared I have to put. It is electric field intensity E bar is equal to what? Rho L by 4 pi epsilon into 0.5 AX minus 1 AY minus 0.5 AZ by mod R whole squared is what? 0.25 plus 1 plus 0.25 is 1.5. Correct? X component squared, Y component squared plus Z component squared. Under root is mod R, whole squared is without root, which is 1.5. Because of which the field intensity at that point is, for a given rho L and for a given medium 4 pi epsilon into 0.5 by 1.5 is 1 by 3 AX minus 2 by 3 AY minus 1 by 3 AZ. These are the 0.5 by 1.5 is 1 by 3. Oh yeah. 1 by 1.5 is 2 by 3. So many volt per meter. One more thing that I want to actually now talk about with respect to the line charge and the field at a point. Mathematically tractable problems only we will take. Suppose I have a charged ring of radius A. And I want to determine, I am not worried about the orientation of it. I just wrote it on a horizontal plane. Ultimately, the statement is, if I have a charged ring of radius A, with charge density rho L or total charge distributed on it is equal to Q. Because it will be uniformly distributed on the ring, Q by 2 pi A will be rho L. They can either give the total charge, that's what is, it can be anywhere on any plane. Because of this, my aim is to talk about the field intensity at a point which is at a distance h from the center on its axis. Generalization. My aim is to determine the field intensity at any point on the axis of a circular line charge of radius A with charge density rho L. Now, when I want to determine this, because the source is a circle, I will take circular coordinates as the coordinates in which I want to do the problem. Without loss of generality, that is why I told you, right? Here in the infinite line charge, whatever may be the line charge given, I will derive the expression with the case considered in the cylindrical coordinate system. I will use the final expression to determine the field of any charge, including the problem I did. My aim is to determine the field at any point on the axis of a circular line charge of radius A having the charge density of rho L. The at any point is at a general distance h from it. I will consider this in cylindrical coordinate system where, listen, at any phi, because the circle is fixed, address is at any phi, let us consider an element at any phi, element subtending angle d phi at center. Having dl is equal to a d phi, phi in radian. At any phi, general case. At any z dz, no. At any phi, element subtending an angle d phi of length dl is equal to a d phi. Rho L dl is the charge. Rho L a d phi is a charge. Now, to determine the electric field intensity at the point of interest, I need to define a vector from the charge to the point of interest. This vector is what? Minus a rho plus h a z. Minus a rho plus h a z will create the field in this direction, dE bar. dE bar. What is dE bar expression now? Differential E bar is equal to rho L a d phi divided by 4 pi epsilon r bar minus a rho plus h a z. A is constant, h is constant, they are not variables, divided by a square plus h square whole power 3 by 2, because the magnitude of this vector is a square plus h square under root whole cubed I have to use. Now which component is to be integrated? Should I integrate both or only one component? For every charge that I considered at any phi, during the integration, there is always a diametrically opposite element that I have to consider. For us to have easy explanation, half of the circle is below, half of the circle is above the page. These two elements are on the page. They are at the same distance, creating the electric field intensity is inclined at the same angle from the vertical. Which component will remain? Which component will remain? Only the vertical component will remain. Horizontal radial component here get cancelled out. This is radial component. Radial components of the elements which are diametrically opposite on the circle get cancelled out. For every element on the circle, there is a diametrically opposite element that is considered during integration, because of which there will be no radial component. I need not integrate radial component. I have to integrate only the axial component, which here is the Z component. Along the axis it goes. So E bar is, hope you are understanding, rho L A H constant 4 pi epsilon A square plus H square whole power 3/2 constant integral d phi. Such elements are to be considered only Az from 0 to 2 pi full circle, because of which it is rho L AH divided by 2 epsilon into A square plus H square whole power 3/2 Az. In this case, Az. The basic thing is what? The field will be along the axis. That's what is the information given. If this is the circular line charge and this is the axis, at this point, the field is along the axis in this direction. At this point, the field is along the axis in this direction, away from the center. Understood? It will be along the axis, away from the center, assuming rho L to be positive at any distance h. Expression is rho L A H by 2 epsilon into A square plus H square whole power 3/2. So many volt per meter.